Right now, somewhere within about 20 light years of where you're sitting, there is almost certainly a rocky planet roughly the size of this one, in the temperate zone of a star reasonably like the Sun. The statistics are solid enough that astronomers will say it out loud, and nobody knows which star. It is not on any list. It has no name. It has never been detected by anything. Meanwhile, the worlds that are on the lists, the ones with the illustrations and the headlines, include a planet that probably has no surface at all, and several that turned out on closer inspection not to exist. Tonight you will find out exactly how far the next habitable planet really is, and by the end you will know why the honest answer has 3 numbers in it, and only one of them is a distance. Get comfortable. If you enjoy finding out that a number you have repeated for years was quietly measuring something else, a slow like and subscribe helps this channel reach more curious minds like you. Because by the end of tonight, 4.24 light years will stop sounding close. Now, let's slowly settle in. There is a number that gets repeated whenever anyone asks how far away the next world might be, and almost everybody who repeats it has never once stopped to ask what it is actually measuring. 4.24 light years. It has the quality of a settled fact. It appears in documentaries and in classrooms and in the captions of photographs, and it is delivered in a tone that suggests the matter has been dealt with. That is the distance to the nearest other place. That is how far you would have to go. The number is correct. Proxima Centauri, a small red star in the southern sky, sits 4.24 light-years from the Sun, and that figure has been measured with a precision that would have seemed like sorcery to the astronomers who first attempted it. It is one of the best established quantities in astronomy. But notice what it is a distance to. It is a distance to a star. It is not a distance to a planet, and it is certainly not a distance to a habitable one. Somewhere in the retelling, over the last decade or so, a substitution happened so quietly that almost nobody noticed it occur. The distance to the nearest star became, in ordinary conversation, the distance to the nearest place we might one day stand. Those are 2 completely different quantities, and only one of them has ever been measured. Tonight we are going to find out what the other one is. Consider how the substitution happened, because it is instructive. In August of 2016, a team of astronomers announced that they had detected a planet orbiting Proxima Centauri. They had been watching the star for months, in a public campaign that posted its observing logs while the data was still coming in, so that anyone who wanted to could watch a discovery accumulate rather than receive it finished. The planet they found has at least a little more mass than the Earth, and it orbits in a place where, under a certain set of assumptions, liquid water could exist on its surface. It was called Proxima b, and within a day the 4.24 figure had been attached to it, and the story had become, there is a possibly habitable world 4 light-years away. Every individual sentence in that story is defensible. The combination of them is where the trouble lives. Because the phrase possibly habitable was doing a very specific and very narrow technical job, and once it left the papers and entered ordinary language, it began doing something much larger and much less honest. Here is a way to feel the size of the gap. If you were handed a list of every planet ever discovered outside our own solar system, and you were asked to sort it into 2 piles, one for planets we know to be habitable, one for planets we do not, the first pile would be empty. Not small, empty. There are more than 6,000 confirmed planets orbiting other stars. The number of them that anyone has established to be habitable is 0. The number of planets in the entire universe that we have ever confirmed to be habitable is 1, and everyone listening to this is currently sitting on it. That is not a pessimistic framing. It is not a rhetorical trick. It is the plainest possible description of the state of the evidence, and it sits directly underneath every headline about second Earths that has ever been published. Which brings us to the most instructive example in the whole field, and it is one that many people still carry around without knowing it has expired. On the 5th of December 2011, NASA announced that the Kepler Space Telescope had confirmed its first planet in the habitable zone of a star similar to our Sun. The planet was called Kepler 22b. It orbits its star once every 289.9 days, which is remarkably close to a terrestrial year, and its star is a G-type star only slightly cooler than our own. The parallels were almost too neat. The coverage was enormous. Artists produced renderings of a blue and white world with continents and cloud systems, and those renderings went everywhere, and to a significant degree they are still going. Kepler 22b is about 620 light-years away, and depending on which reduction of the Gaia astrometric data you use, that figure may be closer to 635 or 640. That distance alone should have slowed the enthusiasm somewhat. But the distance is not the problem with Kepler 22b. The problem is much more fundamental than that, and it is that we have no idea what the planet is made of. Here is what is actually known. Kepler 22b has a measured radius of about 2.4 times the radius of the Earth. That number is solid. It comes directly from how much starlight the planet blocks when it passes in front of its star. And that is essentially the end of the list. Its mass has never been measured. Every attempt has produced only an upper limit, quoted at various times as somewhere below 36 or 52 Earth masses, which is a bound so loose that it excludes almost nothing at all. A planet with a known radius and an unknown mass is a planet with an unknown density, and a planet with an unknown density is a planet whose basic nature is undetermined. Rock or gas, surface or no surface, shore or no shore. And when you look at where 2.4 Earth radii falls in the population of known planets, the news gets worse rather than better. In 2017, a survey remeasured the host stars of the Kepler planets with much greater precision, and because a planet's radius is measured relative to its star's radius, sharpening the stars sharpened the planets. When that was done, something appeared in the data that had previously been smeared out by measurement error. There is a gap. Planets cluster below about 1.5 Earth radii, and they cluster above about 2 Earth radii, and in between there is a valley where comparatively few planets live. The interpretation of that gap is now reasonably well accepted. Below it, planets are overwhelmingly bare rock. Above it, planets overwhelmingly carry thick envelopes of hydrogen and helium, small worlds wrapped in atmospheres thousands of kilometers deep, with pressures at the bottom so extreme that the distinction between gas and liquid stops being meaningful long before anything solid appears. There is no surface. There is no place to stand. There is only a gradient that gets denser and hotter as you descend, until you are somewhere that has no name in ordinary language. Kepler 22b at 2.4 Earth radii sits above the gap. On the statistics, the likelihood that it is a small world with a crushing envelope is at least as high as the likelihood that it is a rocky one, and by most readings it is higher. The first habitable zone planet ever confirmed around a sun-like star, the one on all the posters, the one people still name when asked to name a second Earth, is more likely than not to be a place where the concept of ground does not apply. Nobody hid this. The qualifications were published as diligently as the original announcement in the ordinary literature by the ordinary process. But corrections do not travel the way announcements do. A demoted planet keeps its artwork. It keeps its place in the popular imagination. It keeps its headline, and the headline outlives the finding by decades. So we begin with a small and slightly uncomfortable realization. The number most people carry for how far away another habitable world might be was never measured to the thing they think it was measured to. 4.24 is the distance to a star. 620 is the distance to a planet whose composition is unknown and probably disqualifying. Neither of them is an answer to the question. The question is worth stating precisely, because the precision is what makes the rest of tonight work. How far away is the nearest planet where a human being could stand on solid ground, under a sky, in an atmosphere, beside liquid water, and survive? Not the nearest star, not the nearest planet, not the nearest planet in a habitable zone, the nearest habitable planet. That question has an answer. It is a real answer, and it is more specific than you might expect, and it involves a number that has been calculated by several independent groups working from the same underlying data. By the end of tonight you will know exactly what that number is, but you will not get it yet, and the reason you will not get it yet is that the number by itself is almost meaningless. Handed to you now, it would sound either reassuring or discouraging, and it would be neither, because the distance to the nearest habitable planet turns out not to be the kind of quantity you can state in a single unit and be finished with. There are 3 separate numbers hiding inside it, and only one of them is measured in light years. The other 2 are measured in things that are much stranger and much harder to hear. So we're going to walk out from here. We're going to start with the nearest candidate anyone has, 4.24 light years away, and we're going to apply the same filter to it that quietly disqualified Kepler 22b. Then we will go to the next one, and the one after that, out through 11 light years and 12 and 18 and 31 and 40 and 49, and at each rung we will ask the same simple question and see what survives it. Before any of that, though, there is a phrase that needs taking apart. It has appeared 4 times already in this script, and every single time it has been carrying more weight than it can bear. Habitable zone. Almost nobody who uses that phrase knows what it actually refers to, and what it refers to is not the planet. The idea has a history, and the history explains the confusion. In 1959, an astronomer named Sushu Huang published work on what he called the habitable zone, the range of orbital distances around a star at which a planet could hold liquid water on its surface. It was a genuinely useful idea in an era when there was no other way to think about the problem, because it converted an impossible question, is there life out there, into a tractable one. Where would you have to be, relative to a star, for water to be a liquid rather than a gas or a solid? In 1993, James Casting, Daniel Whitmire and Ray Reynolds gave the concept its modern climate model treatment, and Ravi Kopparapu and colleagues refined the boundaries again in 2013 and 2014. The modern version has 2 edges, and both of them are worth understanding, because both of them are about physics that has actually happened, somewhere, to a real planet. The inner edge is set by the runaway greenhouse. Move a world with oceans slightly closer to its star and the surface warms slightly. Warmer surface means more evaporation. More water vapour in the atmosphere means a stronger greenhouse effect, because water vapour is an extremely effective greenhouse gas. Stronger greenhouse means a warmer surface, which means more evaporation. At some point that loop stops being a gentle feedback and starts being a runaway. The oceans do not gradually shrink. They go into the atmosphere entirely, and then ultraviolet light from the star splits the water molecules apart high up, and the hydrogen, being light, escapes to space. The oxygen stays behind or reacts with the crust, and when the hydrogen is gone, the water is gone permanently, because you cannot put an ocean back together without its hydrogen. That is not a hypothetical. That is the leading account of what happened to Venus, a planet in our own system, nearly identical to Earth in size and mass, which today has a surface temperature of about 737 Kelvin under an atmosphere of carbon dioxide at 92 times Earth's sea level pressure. Lead melts there. The atmosphere alone would crush a submarine. The outer edge is set by the opposite failure. Move the world further out and the surface cools, and a planet's natural response, over geological time through volcanism and the weathering of rock, is to accumulate carbon dioxide in its atmosphere, which warms it back up. That is a real thermostat, and on Earth it has been running for billions of years. But it has a limit. Push far enough out and even a thick carbon dioxide atmosphere cannot hold the surface above freezing, partly because carbon dioxide begins to scatter light back to space rather than trapping heat, and eventually because the carbon dioxide itself starts condensing out of the air and falling as snow. Past that point, nothing you can do with atmosphere saves you. Between those 2 failures lies the zone. And now here is the thing that almost never gets said, the thing that quietly undermines a decade of headlines. The habitable zone is a property of the star. It is calculated from the star's luminosity and its spectrum and the geometry of an orbit. It tells you where a planet would have to be. It does not tell you anything whatsoever about whether a particular planet sitting in that location is habitable, because the calculation assumes a planet with an Earth-like atmosphere. It has to assume that. Without that assumption, the equations have too many free parameters, and the answer becomes anything you like. So a planet in the habitable zone with no atmosphere at all is a frozen rock with a sunlit face, and its equilibrium temperature is far below freezing everywhere. A planet in the habitable zone with 100 bars of carbon dioxide is a furnace. A planet in the habitable zone with a hydrogen envelope thousands of kilometers deep has no surface for water to sit on. The zone is a statement about real estate. It says nothing about the house, and in fact it does not even establish that there is a house. We have a control experiment for this, and it is embarrassingly close to home. Venus, Earth and Mars are all in or very near the Sun's habitable zone, depending on which version of the boundaries you use. 3 planets, 1 zone. One of them is a crushing furnace. One of them is a cold desert with an atmosphere of about 6 millibars, less than 1% of ours, so thin that liquid water on the surface would boil and freeze almost simultaneously. and one of them is covered in oceans and has been continuously inhabited for something like 3.5 billion years. The differences between those three outcomes are driven by mass, by magnetic field, by volcanic and tectonic history, by how much water each one started with and how much it managed to keep, and by the accidents of what hit them and when. Not one of those properties is measurable at 40 light-years by any instrument that currently exists or is currently funded. We can locate the zone with great confidence. We cannot tell which of the three outcomes a planet inside it has had. It is worth sitting with the thermostat for a moment, because it is the single most important thing about the Earth that nobody can check on anybody else's planet. It is called the carbonate-silicate cycle, and it works like this. Carbon dioxide in the air dissolves into rainwater and falls as a weak acid. That acid slowly dissolves silicate rock, and the products wash into the ocean, where marine organisms and simple chemistry lock the carbon into carbonate minerals that settle to the seafloor. Plate tectonics then carries that seafloor down into the mantle, where heat and pressure drive the carbon back out through volcanoes as carbon dioxide, and the cycle begins again. The loop takes something on the order of 100 million years to turn over once, and here is the elegant part. When the planet warms, weathering speeds up, which draws carbon dioxide out of the atmosphere faster, which cools the planet. When the planet cools, weathering slows, volcanoes keep supplying carbon dioxide, and the atmosphere warms back up. It is a thermostat that nobody designed, and it has been holding Earth's surface within a livable range through billions of years of increasing solar output. Now notice what it requires. It requires liquid water for the weathering. It requires plate tectonics for the return leg, which requires a mantle still hot enough to convect, and a crust wet enough to be flexible. It requires an ocean, and a carbon reservoir and an interior heat engine, all running simultaneously for geological ages, and there is currently no proposed method, not with existing telescopes, not with the ones being built, not in any funded concept, for detecting whether a planet 40 light-years away has plate tectonics. The thing that most plausibly separates a living world from a dead one in the same orbit is entirely invisible from here. There is one more complication, and it matters because it changes which planets end up on the list you read. There are two habitable zones in common use. The conservative habitable zone uses the runaway greenhouse and maximum greenhouse limits directly out of the climate models. The optimistic habitable zone widens both boundaries, and it does so on empirical grounds. Venus appears to have lost its surface water at least 1 billion years ago, which suggests the inner edge is closer in than the models say, and Mars appears to have had liquid water on its surface around 3.8 billion years ago, when the Sun was fainter, which suggests the outer edge is further out. Both widenings are defensible. They are also not the same zone. Which version a given paper uses changes the guest list. Several planets that appear routinely on popular lists of habitable zone worlds are inside the optimistic zone and outside the conservative one, which is to say that whether they are in the habitable zone at all depends on which of two reasonable definitions you happen to be using that day. That is not a scandal either. It is just the ordinary looseness of a term that was coined when the alternative was total ignorance, and which is now being asked to carry far more weight than it was built for. Several researchers have argued, quietly and without much success, for retiring the phrase altogether, for calling it the temperate zone, or the liquid water zone, or simply the circumstellar habitable zone, with the emphasis firmly on the circumstellar part. The argument is that the word habitable has done more damage than good, because in ordinary English habitable means a place you could live, and in astronomy it means a distance from a star at which a hypothetical planet with an assumed atmosphere could hold an assumed ocean. Those are not the same word. So here is the discipline that we are going to carry through the rest of tonight, and it is worth saying it in a form short enough to remember, because we are going to come back to it. A candidate is not a destination. Every world we are about to walk past is a candidate. Not one of them is a destination, and the distance between those two categories is not measured in light years at all. It is measured in unfinished measurements, in masses that are only minimums, in radii that have never been obtained, in atmospheres that have never been detected, in compositions inferred from population statistics rather than observed directly. Each of those gaps is a place where a candidate can quietly stop being one, which is exactly what we are going to watch happen, starting with the nearest one there is. Because there is a planet 4.24 light-years away, and it has been sitting there in the popular imagination for a decade now, as the obvious first stop, the nearest door, the one we would go to if we ever went anywhere. And it is a real planet. Nobody disputes that it exists. The question is whether the door opens. Proxima Centauri is not a star you can see. That surprises people. It is the closest star to the Sun, and it has been the closest star to the Sun for a very long time, and it is completely invisible to the naked eye from anywhere on Earth. Its apparent magnitude sits around 11, and the human eye tops out at about 6 under a genuinely dark sky. You would need a telescope to find the nearest star in the universe. The reason is that Proxima Centauri is small. It is a red dwarf of spectral class M 5.5, with about 12% of the Sun's mass and about 15% of its radius. Its surface temperature is around 3042 Kelvin, roughly half the Sun's, so it radiates most of its energy in the infrared, where our eyes do not work. Its total output is something like 1/1700th of the Sun's luminosity. If you swapped it for the Sun tomorrow, the sky would not simply be dimmer. It would be dark, and the ground would be frozen within days. That faintness is why Proxima b is where it is. The planet, announced in August of 2016 by Guillem Anglada Escudé and the pale red dot team using the HARPS and UV spectrographs, orbits its star every 11.186 days at a distance of about 0.0485 astronomical units. That is roughly 7.5 million kilometers, about 5% of the distance between the Earth and the Sun, and comfortably inside the orbit of Mercury if you dropped it into our system. In our system, it would be a cinder. Around Proxima, it receives about 65% of the light Earth receives, which places it inside the habitable zone. Its minimum mass is about 1.07 times the Earth's, refined by later observations with the espresso spectrograph to something closer to 1.17, with some catalogues quoting 1.27. Note the word minimum. We will come back to that word because it is doing an enormous amount of work. So, a roughly Earth-mass planet in the habitable zone, orbiting the nearest star to our own. It is genuinely difficult to imagine a more encouraging headline, and for about a week in 2016, that is exactly how it read. Then the specifics arrived. At 0.0485 astronomical units, the tidal forces between a planet and its star are enormous, and they act to synchronize the planet's rotation with its orbit. The timescale for that synchronization is far shorter than the age of the system, which means Proxima b is almost certainly either tidally locked or caught in some spin-orbit resonance. One face permanently toward the star, one face permanently away, no sunrise, no sunset, no day in the sense that any living thing on Earth has ever experienced a day, and Proxima Centauri is a flare star. This is where the picture stops being merely difficult and starts being genuinely hostile. In March of 2016, the Everoscope array recorded a superflare that briefly brightened the star by a factor of about 68 in visible light. 3 years later, in May of 2019, a coordinated observing campaign that included the ALMA array caught something considerably worse, an event in which the star brightened by roughly 14,000 times in the near ultraviolet, and did so over the course of about 7 seconds. 14,000 times in 7 seconds. From a star whose planet sits at 5% of an Earth-Sun distance. Let me place you there for a moment. You are standing on the line, not on the day side and not on the night side, but on the terminator, the boundary between them, which on a tidally locked world is not a moving line at all. It is a permanent geographic feature, a ring around the planet. Behind you, the night hemisphere, where anything capable of freezing has long since frozen and stayed that way. Ahead of you, the day hemisphere, where it is noon, and has been noon since before there was anything here to notice. The star hangs on the horizon. It does not rise. It does not set. It is roughly 3 times the apparent width of our sun in your sky, and it is a dull, sullen red, and it is not moving, and it has not moved for 4 billion years. The light is strange in a way that is hard to name at first, and then you place it. Most of the star's output is infrared, so the landscape is warmer than it is bright. You can feel heat on your face from something that looks dim, and then, with no warning of any kind, the star flares. In the space of 7 seconds, the ultraviolet output climbs by a factor of 14,000. There is no sound and very little visible change. This is happening in wavelengths your eyes cannot register, and nothing on the surface without shielding would come through it intact. Then it fades, and the star settles back, and it goes on hanging exactly where it was, and the only reasonable response is the realization that this will happen again, and there is no season, no cycle, no way to know when. That is the nearest door. The flares are not merely a hazard to anything standing on the surface. They are a hazard to the surface itself, or rather to the air above it. The extreme ultraviolet flux at Proxima B's orbit is estimated at hundreds of times what Earth receives from the Sun. Over billions of years, radiation at that intensity does something specific to an atmosphere. It heats the upper layers until the lightest molecules reach escape velocity and stream away. That process removes hydrogen first, but sustained long enough, at high enough intensity, and with a weak or absent planetary magnetic field to deflect the stellar wind, it will also strip heavier species. Oxygen, nitrogen, the things an atmosphere is actually made of. Whether Proxima b has retained any atmosphere at all is not a settled question, and it is not a minor one. It is one of the genuinely open problems in the field. There is no observation that answers it, because the planet does not transit its star from our viewing angle, which means the technique that could sample its atmosphere is unavailable to us. We know the planet is there because of how it tugs its star. That tug is essentially the entire body of evidence. There is a further problem, and it is one that operates on a timescale long enough that it may have decided the outcome before the planet was 100 million years old. Red dwarfs do not arrive on the main sequence at their final brightness. They spend an extended youth considerably more luminous than they will later be, contracting slowly and burning through a phase that can last hundreds of millions of years. During that phase, the habitable zone is much further out than it will eventually settle, which means a planet that sits comfortably in the zone today may have spent its entire first-era interior to it, in a runaway greenhouse, with its oceans in the atmosphere and ultraviolet light steadily splitting the water and letting the hydrogen escape. Models of this process suggest that planets around late red dwarfs can lose the equivalent of several Earth oceans of water this way, before the star ever calms down. By the time the habitable zone arrives at the planet, there may be nothing left for it to be habitable with. And this is a good moment to say plainly what that word minimum has been doing. The radial velocity method measures how fast the star moves toward and away from us as the planet swings it around their shared centre of mass. But we only see the component of that motion along our line of sight. If the planet's orbit happens to be edge onto us, we see the full wobble, and the mass we calculate is the real one. If the orbit is tilted, we see only a fraction of the motion, and the mass we calculate is too low. And there is no way, from the wobble alone, to tell the difference between a light planet in an edge-on orbit and a considerably heavier planet in a tilted one. So what comes out of the calculation is not the mass. It is the mass multiplied by the sine of an angle we do not know. It is a flaw. Proxima b is at least about 1.1 times the mass of the Earth. It could be 2. It could, at unlucky enough inclinations, be several. In fairness, it is not all bad news, and the honest version of this includes the arguments on the other side. Climate models of tidally locked worlds have been run repeatedly over the last 2 decades, and they do not all end in disaster. A planet with a sufficiently thick atmosphere can transport heat from the day side to the night side efficiently enough to keep the whole surface above freezing and prevent the atmosphere from collapsing and snowing out on the dark hemisphere. An ocean does the same job even better because water moves heat extremely well. The resulting configuration is sometimes called an eyeball world, a permanently sunlit region of open water at the substellar point, surrounded by a ring of ice with a habitable band running around the terminator. It is not Earth, but it is not nothing, and it is a serious possibility rather than a consolation prize. The system holds more than one planet. In 2022, a third signal was confirmed as Proxima d, a very small world of about 0.26 Earth masses on a 5.12-day orbit, well inside the habitable zone's inner edge. There is also a disputed candidate, Proxima c, at roughly 1.5 astronomical units on a 5.2-year orbit, which would be far outside the zone and frozen. And there is a further wrinkle worth carrying. Proxima Centauri itself orbits the Alpha Centauri A and B pair at a distance of about 0.2 light-years, with a period somewhere around 550,000 years. The nearest star is only the nearest star for this era. On long enough timescales, even that number moves. So we have applied the filter to the closest candidate there is, and here is what came out the other side. A planet that certainly exists. A planet with a minimum mass close to Earth's, whose true mass is unknown because we cannot measure the orbital inclination. A planet whose radius has never been measured, which means its density has never been measured, which means we do not know whether it is rock or something else. a planet almost certainly locked with one face to a star that periodically brightens 14,000-fold in ultraviolet. A planet whose atmosphere may have been stripped away before multicellular life existed on Earth, and which we currently have no way to check. 4.24 light-years, the nearest door in the universe, and we cannot tell from here whether there is anything behind it. And that is not an unusual result. That is what happens to every single one of them. There is a filter operating on this entire question, and it is worth understanding exactly how it works, because once you see the mechanism you will start to see it everywhere, including in some very famous places where it has already done its work quietly years ago, without anybody noticing. Almost everyone carries an unexamined assumption about how discovery works. The assumption is that it accumulates, that the list of known things gets longer, never shorter, that the frontier moves in one direction only, that once a thing is found, it stays found. The catalogue of nearby habitable worlds does not behave that way. Entries leave it. Some of the most famous entries have already left it, and if you have not been following the literature closely, you are almost certainly still carrying several of them around. In September of 2010, a planet called Gliese 581g was announced at a distance of about 20.4 light-years. It was described at the time, with considerable justification, as the first planet ever found squarely in the middle of a habitable zone, rather than teetering on an edge. It was the best candidate anybody had. It had a name, it had press, it had illustrations. Independent teams then went to look for the same signal in their own data and could not find it. Over the following years, the periodicity was traced to something else entirely, the star's own magnetic activity, aliased into the radial velocity measurements by the star's rotation. Dark star spots rotating into and out of view distort the shapes of spectral lines in a way that looks, to the analysis, almost exactly like a Doppler shift. The planet was the star's own face turning. Gliese 581d, a second world claimed in the same system, followed a similar arc. Announced, contested, defended, contested again, and never resolved to general satisfaction. In 2014, a planet called Captain B was announced at about 12.8 light-years, and its story was even better. Captain Star is a halo star, moving retrograde through the galactic disk at over 250 kilometers per second, and it is thought to be a stripped remnant of a small galaxy the Milky Way consumed long ago. It is roughly 11 billion years old. So the announcement was not merely of a habitable zone planet nearby, but potentially of the oldest habitable world ever identified, a place that had been sitting in its star's temperate zone for more than twice the age of the Earth, with all the time in the universe for something to happen on it. In 2015, Paul Robertson and colleagues showed that the signal's period matched the star's rotation period. It was the same failure mode. There was no planet. The Gliese 667c system was at one point claimed to hold as many as 7 planets, 3 of them in the habitable zone, which would have made it the richest temperate system known. Later reanalyses reduced that to 2 or 3 planets total, with the habitable zone claims for most of the others withdrawn. None of this is a scandal, and it is important to be clear about that. This is exactly what a healthy field looks like from the inside. The corrections were published by the same journals, through the same process, often by researchers who had been part of the original work. Nobody covered anything up. The self-correction is the system functioning correctly, at the very edge of what the instruments can do, which is precisely where you would expect claims to be fragile. But there is a consequence, and it is the uncomfortable one. Corrections do not travel the way announcements do. A demoted planet keeps its artwork, it keeps its Wikipedia illustration, and its documentary appearance, and its place in the list somebody memorized in school. The retraction is a paragraph in a specialist journal. The announcement was a global news cycle. So the list that exists in the general public's mind is not the current list. It is the union of every planet ever announced, minus none of them. Which means that almost everyone alive right now is holding a map of the nearby universe, with places on it that were erased years ago, and has no idea which ones. It is worth sitting with that for a second, because it is a stranger feeling than it first appears. Being wrong about something is ordinary. Everyone is wrong about things, but this is a different shape of wrongness. This is holding a belief that was correct when you acquired it, that was acquired from a legitimate source, that was never contradicted anywhere you were likely to be looking, and that stopped being true at some point you cannot identify. There was no moment when you learned the wrong thing. There was only a moment somewhere when the thing you already knew quietly stopped being the case, and nobody came to tell you. Multiply that across the whole subject. A reasonable estimate is that somewhere between a third and a half of the habitable world announcements made between 2010 and 2015 have since been demoted, revised, contested, or reinterpreted in ways that would have changed the headline. The popular record carries essentially none of that, which means that the confidence most people feel about how many nearby habitable planets have been found is not merely a little too high. It is calibrated against a version of the catalogue that no longer exists. Now, the filter itself. What exactly is it that keeps doing this? It comes down to a very small number of measurable quantities and the gaps between them. If a planet transits its star, passes directly in front of it from our angle, we measure how much light it blocks, and from that we get a radius. If a planet tugs its star measurably, we get a minimum mass. Almost every known planet gives us one of those two numbers. A small minority give us both. And it is only when you have both that you get the quantity that actually decides everything, which is density. Density is the whole game, because density is the difference between rock and gas. It is the difference between a world with a surface, a shoreline, a horizon, an atmosphere sitting on top of solid ground, and a world that is essentially a small hot core buried under thousands of kilometers of hydrogen and helium, where the pressure rises so smoothly that there is no boundary anywhere between what you would call air and what you would call ocean, and no point at which anything you could stand on ever appears. And in 2017, a survey remeasured the host stars of thousands of Kepler planets with far greater precision, and because planetary radii are derived relative to stellar radii, the planets sharpened when the stars did. What emerged was a feature that had previously been blurred out by measurement error. Planets cluster below about 1.5 Earth radii. Planets cluster above about 2 Earth radii, and in between there is a valley, a genuine deficit, a range of sizes that planets seem to avoid occupying. The interpretation is now fairly well established, and it is physical rather than statistical. Small rocky planets that formed with hydrogen envelopes lose them, because the envelope is only weakly bound, and stellar radiation strips it away over the first hundreds of millions of years. Larger planets hold on to theirs, so you end up with two populations, stripped bare rock below and enveloped worlds above, and comparatively little in between, because the in-between state is unstable. The valley is the fingerprint of a process that has been sorting planets into two categories for the entire history of every system we can see. The consequence for our question is severe. A planet's radius, on its own, does not tell you which side of that divide it sits on if it lands anywhere near the boundary. And a planet above the boundary is not a slightly larger Earth. It is a completely different kind of object with no surface at all. This is what happened to Kepler 22b, quietly, over about a decade. Not a retraction, the planet certainly exists, but a reclassification by implication. 2.4 Earth radii puts it above the valley. Its mass has never been measured. So the world that is still, 15 years later, the one people name when asked to name a second Earth, is more likely than not to be a place where the word ground has no referent, and Kepler 22b is not an isolated case. Kepler 186f, announced in 2014 at about 580 light-years, was the first Earth-sized planet found in a habitable zone. 1.17 Earth radii, close enough to our own size that the comparison genuinely holds. More than a decade later, its mass has still never been measured. Its star is faint and distant, and the wobble is far too small for any spectrograph now operating. So Kepler 186f remains what it was on the day it was announced, a radius and an orbital period, and nothing else. It is not a world. It is two numbers. Out of more than 6,000 confirmed planets, the number that sit in the conservative habitable zone and have both a measured mass and a measured radius, the two numbers you need before you can say anything at all about what a place is made of, is in the single digits. And there is a structural version of this problem that is worse than any individual case, because it applies to the entire neighbourhood at once. Roughly 70 to 75% of the stars within 30 light-years of the Sun are red dwarfs. That is simply what this part of the galaxy is made of. So if you want a nearby habitable planet, the overwhelming probability is that you're going to find it orbiting a red dwarf, because that is where the planets near us are. And red dwarfs are, on multiple independent counts, the worst available hosts. Their habitable zones are only a few hundredths of an astronomical unit out, because the stars are so faint, which means strong tidal torques and near-certain locking. It means sitting inside the star's flare environment rather than at a safe remove. It means an extended, violently active youth that can last billions of years, where the sun settled into its quiet rhythm within a few 100 million. And it means the pre-main sequence desiccation problem, the possibility that the ocean was boiled away before the star ever calmed down. So the geometry of our own neighbourhood is working against us. The stars that are near are the stars that are bad. The stars that are good, steady, quiet, sun-like, with wide habitable zones far enough out to avoid tidal locking, are comparatively rare and therefore comparatively far. Which sets up the walk we're about to take. We're going outward now, rung by rung, from 4 light-years to 50, and at every step there is a trade being made. Each step buys a slightly better planet, or a slightly quieter star, or a slightly firmer measurement, and each step costs something that turns out in the end to matter more than any of it. The next rung is at about 11 light-years, and its virtue is quiet. Ross 128b was announced in 2017 from radial velocity data, taken with the HARP spectrograph in Chile. It has a minimum mass of around 1.4 Earth masses and an orbital period of 9.9 days. What makes it interesting is not the planet at all, it is the star. Ross 128 is a red dwarf, like Proxima, but it is an unusually calm one. It flares rarely. It does not appear to have the violent chromospheric activity that makes Proxima Centauri such a difficult neighbour, and it is old enough that whatever youthful temper it had has long since burned out. If you were designing a red dwarf to host a habitable planet, you would design something close to Ross 128. The problem is where the planet sits. It receives about 1.38 times the light Earth receives from the Sun. That places it at, or just inside the inner edge of the conservative habitable zone. Depending on which set of atmospheric assumptions you feed into the models, Ross 128b is either a temperate world on the warm side, or it is the beginning of a runaway greenhouse. There is no observation that distinguishes those two possibilities. There is a minimum mass, an orbital period, and a stellar spectrum, and everything else is inference. At about 12.36 light-years there is Luiten b, also catalogued as GJ273b, announced in 2017 with a minimum mass near 2.89 Earth masses on an 18.65-day orbit. 2.89 Earth masses is a number that should make you pause slightly, because it is drifting toward the size range where an envelope becomes plausible, and again, no radius, no density, a wobble and an inference. Then, at about 12.5 light-years, comes the entry that once sat at the very top of the entire catalogue. Teegarden's star is an M7 dwarf with about 9% of the Sun's mass, one of the coolest and faintest objects in the entire solar neighbourhood, so dim that it was not catalogued at all until 2003, despite being one of our 24 nearest stellar neighbours. In June of 2019, the Kármán survey announced 2 planets around it. Teegarden's star B has a minimum mass of about 1.05 Earth masses on a 4.91-day orbit. Teegarden's star C has a minimum mass of about 1.11 Earth masses on an 11.4-day orbit. Both of those minimum masses are almost exactly Earth's. That is unusual, and it produced an unusual number. There is a metric called the Earth Similarity Index, which combines radius, density, escape velocity and surface temperature into a single figure between 0 and 1, where 1 is Earth. On the initial data, Teegarden's star B scored somewhere around 0.95 to 0.97, the highest score anything in the catalogue had ever achieved, near perfect, and it was reported that way widely. Later data revised the score down to roughly 0.9, and subsequent reanalyses have adjusted the system's parameters further and added a third candidate planet. But the more useful thing to know about that index is what goes into it. Of the 4 quantities it combines, 3 are usually estimated rather than measured for the planets it ranks. It is not a measurement. It is a weighted summary of a set of assumptions, and it can be a very high number for a planet whose radius nobody has ever obtained. At about 18 light-years is the newest arrival, and the one that prompted this whole survey. On the 23rd of October, 2025, a team led by researchers at the University of California, Irvine published in the astronomical journal the discovery of GJ251c. They found it using 2 purpose-built instruments, the Habitable Zone Planet Finder at the Habitable telescope in Texas and NIDI at the Wind telescope at Kitt Peak, spectrographs designed from the ground up around a specific difficulty, which is that the nearest stars are cool and red and emit most of their light in the infrared, exactly where the older generation of optical spectrographs is least sensitive. An entire class of instrument had to be built before the nearest stars could be studied properly at all. The signal corresponds to a period of about 53.647 days and a minimum mass of roughly 3.84 Earth masses. The star sits about 5.5 parsecs away, which is approximately 18 light-years. And the Discovery paper makes a claim that is worth attending to carefully. GJ 251c is currently the single best candidate for direct imaging of a terrestrial habitable zone planet anywhere in the northern sky. Direct imaging means resolving the planet as its own point of light, separate from the star, not inferring it from a wobble or a shadow, but actually seeing it. Nothing that exists today can do that for a planet this small around a star this close. The next generation of 30-meter class ground telescopes may be able to. That is the significance of the announcement. Not that a habitable world has been found, but that a target has been identified which the instruments of the 2030s might be able to look at directly. And notice, again, what is missing. GJ 251c does not transit. No radius, no density. A minimum mass of 3.84 Earth masses, which is comfortably in the range where a substantial envelope is possible. The paper is careful. It calls it a candidate. The 53.647-day period is actually a point in the planet's favour, and it is worth saying why. A longer period means a wider orbit. A wider orbit around a red dwarf means weaker tidal torques, so locking is less certain, and it means the planet sits further from the star's flares, so the radiation dose per unit time is lower. Most red dwarf habitable zone planets orbit in a week or two. 53 days is a comparatively generous distance, and it is the kind of detail that separates a real target from a headline. Continuing outward, at about 23.6 light-years is Gliese 667cc, with a minimum mass near 3.8 Earth masses on a 28.1-day orbit, announced between 2011 and 2012, and it is the survivor of the system that was once claimed to hold 7 planets, and now holds 2 or 3. At about 31 light-years is Wolf 1069b, announced in 2023 by Carmenes, with a minimum mass of 1.26 Earth masses, an estimated radius around 1.08 Earth radii, and a 15.6-day orbit, around a star that appears comparatively quiet. It is one of the better-looking entries on the list, and the estimated radius is exactly that, estimated from models, not measured. And at about 40 light-years, something changes. Gliese 12b was announced in May of 2024 from data taken by the TESS survey satellite, and it transits. That single fact makes it a different category of object from everything we have discussed since Proxima. Because it passes in front of its star from our angle, its radius is a measurement rather than a model output, about 0.96 Earth radii, slightly smaller than Earth, firmly, unambiguously below the radius valley, which means it is rock, not probably rock. Its orbital period is 12.76 days, its equilibrium temperature is estimated at about 315 Kelvin, and its host is a quiet red dwarf. And crucially, because it transits, it is accessible to the one technique that could tell us whether it has an atmosphere. That is the trade the ladder has been making all along, and this is the rung where it becomes visible. The nearest planets are the ones we can weigh but not see. The transiting planets are the ones we can see but not reach. And the transiting ones are further away not because transiting planets are rare at close range, but because of pure geometry. A planet only transits if its orbital plane happens to line up with our line of sight, and most of them do not. For a planet in an Earth-like orbit around a Sun-like star, the geometric chance of that alignment is about 0.47%, fewer than 1 in 200, which means that even if every Sun-like star in the galaxy had an Earth, a perfect transit survey would find fewer than 1 in 200 of them, and all the rest would be permanently invisible to that technique. There is one more entry worth naming before we stop, and it is much further out, about 101 light-years. TOI 700d was announced in January of 2020, the first Earth-sized planet in a habitable zone found by the TESS survey, at 1.07 Earth radii on a 37.4-day orbit. 3 years later, in January of 2023, a fifth planet was found in the same system. TOI 700e at 0.95 Earth radii on a 27.8-day orbit, sitting in the optimistic habitable zone. 2 Earth-sized planets in or near the temperate zone of the same star, both with measured radii. It is one of the most genuinely encouraging systems known. It is also 101 light-years away, which for the purposes of any follow-up observation of its atmosphere is effectively out of range. The signal from a planet that's small, around a star that far, is below what any instrument can extract, and it is worth mentioning what is conspicuously not on this list. Tau Ceti sits at about 11.9 light-years and is the nearest single star genuinely similar to the Sun. A G-type star, stable, quiet, not a red dwarf, with a wide habitable zone far enough out that tidal locking is not a concern. It is, on paper, the neighbourhood's best host. Planets have been claimed around it, some near the edges of its habitable zone, though the claims have been revised repeatedly, and the surviving candidates have minimum masses around 4 Earth masses. But Tau Ceti carries something else, a debris disk roughly 10 times as massive as our own systems, 10 times the leftover rubble, 10 times the impact rate sustained over billions of years on anything with a surface. The nearest genuinely sun-like star in the sky may well be a shooting gallery. So the catalogue we have been walking through is not a list of the habitable planets near us. It is a list of the habitable zone planets near us that happen to be detectable by one of 2 methods, each with its own strong and quite different bias. The radial velocity method favours heavy planets on short orbits, which is why the nearby list is full of super-Earths around red dwarfs, and contains essentially nothing resembling an Earth around a sun. The transit method favours planets whose orbits happen to be edge-on, which is a lottery. We have now climbed from 4 light-years to 40. Every rung has been a candidate. Not one of them has been a destination, but 2 more remain, and they are different from everything that came before, because for the first time there are actual answers within reach. Not inferences, not models, not indices, but measurements that could genuinely settle whether one of these places has air. On the 22nd of February 2017, a team led by Michael Gillen announced that a small cold star 40.7 light-years away had 7 Earth-sized planets orbiting it. Not 1, not 2, 7. The star is TRAPPIST-1, and it is barely a star at all. It is an M8 ultra-cool dwarf with about 9% of the Sun's mass and 12% of its radius, which makes it only slightly larger than Jupiter, though roughly 80 times as massive. Its surface temperature is around 2,566 Kelvin, and its total luminosity is about 1/2000th of the Sun's. It is close to the smallest thing that can be a star, a little less mass, and it would never have started fusing hydrogen at all. Around it, 7 worlds, all between about 75% and 113% of Earth's radius, and they are packed absurdly close. The entire system, all 7 orbits, would fit comfortably inside the orbit of Mercury. The outermost planet completes a circuit in under 19 days. The innermost takes about a day and a half. From the surface of any one of them, the others would appear as disks in the sky, several of them noticeably larger than our Moon appears from Earth, moving visibly against the stars over the course of hours. The orbital periods are not random. They sit in a chain of near resonances, ratios close to 8:5, 5:3, 3:2, 3:2, 4:3, and 3:2 running outward. That pattern is not something that happens by accident. It is the signature of planets that formed further out in a gas disk and migrated inward together, locking into step with each other on the way. The system has an architecture. It was assembled. TRAPPIST-1e is the one that matters. It has a radius of 0.92 Earth radii and a mass of 0.69 Earth masses, both measured, which puts it in that single-digit club of habitable zone planets where we actually know the density. It orbits every 6.1 days and receives about 65% of the light Earth receives, placing it squarely in the conservative habitable zone. Its density is consistent with a rocky composition. The system is around 7.6 billion years old, which is well over half again the age of the Earth. If you were asked to name the single most promising rocky planet in the habitable zone of another star, anywhere in the sky, accessible to instruments that currently exist, TRAPPIST-1e is the answer, and it is not close. The reason is the geometry, and it is worth being precise about, because it is the hinge that everything else in this part turns on. Let me put you in front of the data. You're not looking at a planet. There is no image of TRAPPIST-1e, and there will not be one in your lifetime. What you are looking at is a number plotted against time. A telescope points at the star and measures how much light arrives, second by second, for hours. The number is flat. It wanders slightly with instrumental noise, but it is flat. Nothing is happening. And then, gradually over a few minutes, the number begins to fall. Not by much. It descends by about 0.5%, levels off, holds there for well under an hour, and then climbs back to where it was. That is it. That is the entire event. There is no disk, no silhouette, no black circle crossing a bright one. That image exists only in illustrations. What exists in reality is a shallow dip in a line on a graph, less deep than the thickness of the line in most printed versions of it, and everything descends from that. The planet's size comes from the depth of the dip. Its orbit comes from the spacing between dips. Its place in the habitable zone comes from that orbit combined with the star's brightness. Every hope anyone has attached to TRAPPIST-1e, every observing program, every argument about whether it is the most important object in the sky, all of it rests on a shadow 0.5% deep. And then, if you want to feel the floor tilt properly, 0.5% is enormous. It is one of the deepest transit signals from an Earth-sized planet that anyone has. Earth crossing the face of the Sun, seen from outside, produces a dip of about 84 parts per million. Not 0.5%, 84 millionths, 60 times shallower than the one we're calling large, which means TRAPPIST-1e is not observable because the planet is big. It is observable because the star is tiny. We are not looking at a bright signal. We are looking at a small screen. That single fact explains the entire shape of the nearby catalogue. The habitable zone planets we can actually study are almost all around red dwarfs, not because red dwarfs are good hosts. We have established at length that they are not, but because a planet blocks a much larger fraction of a small star. The population we can examine was selected by the size of the star, and the stars that are small enough to work with are the ones with the worst habitability problems. The observational bias and the habitability problem are the same fact, viewed from two directions. There is something else about TRAPPIST-1 that is easy to pass over and difficult to stop thinking about once you have noticed it. A star that's small burns its fuel with extraordinary parsimony, and it also convects throughout its entire volume, which means it can eventually consume nearly all of the hydrogen it contains rather than just the core. The result is a lifespan measured not in billions of years but in trillions. TRAPPIST-1 will still be burning at roughly its present brightness when every sun-like star in the universe has died and cooled, when the sky, from anywhere, contains nothing but red dwarfs and the dark remnants of everything else. Those 7 planets have something like 100 times the remaining lifetime of the Earth ahead of them. It is also worth knowing how the system was found, because it is a small correction to how discovery is usually imagined. The first 3 planets were detected in 2016 using a 60-centimetre telescope in Chile, an instrument smaller than many amateur setups, dedicated to monitoring a short list of ultra-cool dwarfs. The remaining 4 came out of a follow-up campaign with the Spitzer Space Telescope, which stared at the star for 20 consecutive days. The most planet-rich habitable zone system known to science was found by pointing a modest telescope at an object too faint to see and waiting. And JWST has already delivered a result for the inner planets, which is worth holding on to because it sets expectations. Observations of TRAPPIST-1b and TRAPPIST-1c, published in 2023, measured the heat coming off their day sides and found essentially what a bare rock with no atmosphere would produce. No thick atmosphere on either. Those two are much closer to the star than 1e and were always the least likely to hold on to air, so this does not settle anything about the outer planets. But it is the first direct evidence from real measurements rather than models that the atmospheric stripping problem around red dwarfs is not theoretical. At least twice in that system, it appears to have already happened. The other system is at about 48.8 light-years, and it was found by a project called Mirth, which is worth a moment of its own. Mirth is not a flagship observatory. It is an array of small, essentially commercial-grade telescopes, monitoring nearby red dwarfs for exactly this kind of shallow dip. The discovery of one of the 2 best habitable zone candidates in the sky did not require a billion-dollar facility. It required pointing modest equipment at the right stars, patiently, for years. LHS 1140b was announced in 2017 and has since been revised to about 1.7 Earth radii and 5.6 Earth masses on a 24.7-day orbit. Its star is an M4.5 dwarf, and it is remarkably calm. Unlike Proxima, unlike most of its class, LHS 1140 is a quiet star, which dramatically reduces the atmospheric stripping problem that hangs over every other entry on the list. 1.7 Earth radii puts it at the upper edge of the rocky regime, right at the boundary of the radius valley, and its measured density is where it gets interesting. The density is low enough that a purely rocky composition does not fit comfortably. Models permit a water fraction of perhaps 10 to 20% by mass. Take a moment with that number. Earth's oceans are roughly 0.02% of its mass. A planet that is 10 to 20% water by mass is not a world with oceans. It is a world that is substantially made of ocean. A global sea with no continents anywhere, hundreds of kilometers deep, with a floor of high-pressure ice rather than rock, and no land, no shoreline, no tide pools, no interface between water and stone where the chemistry we associate with the origin of life on Earth is thought to have happened. It might still be habitable. It might be an eyeball world with open water at the substellar point and ice everywhere else. Observations with the James Webb Space Telescope in 2023 and 2024 produced tantalizing hints of a nitrogen-rich secondary atmosphere, possibly with water vapor. Hints, not detections, and the difference between those two words is the subject of the next part. There is also a quieter reason LHS 1140b matters, which has nothing to do with the planet and everything to do with its star. The single largest source of doubt hanging over every red dwarf candidate we have discussed is whether the star tore the atmosphere off before anything could happen on the surface. A calm star does not remove that doubt, but it moves it. It takes the most likely disqualifying mechanism and makes it substantially less likely, which for once means that a non-detection of an atmosphere would actually mean something. Around Proxima, finding no atmosphere would tell you almost nothing you did not already suspect. Around a quiet star like this one, it would be genuine information. So there they are, the two that matter most. Two specific points of light, 40 and 49 light-years out, both transiting, both around quiet enough stars, both with measured masses and measured radii, both sitting in a habitable zone. Out of 6,000 planets and 30 years of searching, these are the two where the question could actually be answered. The James Webb Space Telescope has been pointed at both of them, the most powerful observatory ever built, aimed at the two best candidates in the sky, for multiple observing campaigns across several years, and here is what it has been able to tell us about whether either of them has an atmosphere. Let us step back for a moment and stack up what we have, because we are about to add a piece that changes the shape of all of it. We began with a number, 4.24 light-years, and found that it measures the distance to a star, not to a planet, and certainly not to a habitable one. We took apart the phrase habitable zone, and found that it describes the star as well, not the planet, and that in our own system 3 worlds sit in or near it with 3 completely different outcomes. We applied that filter to the nearest candidate and found a world that may be locked, may be stripped, may have lost its water before the star ever settled down, and whose true mass we cannot determine. We watched the catalogue shrink as well as grow. Gliese 581g, Captain B, most of Gliese 667c. We climbed outward through 11 light-years and 12 and 18 and 31 and 40, and found that each rung offered a slightly better planet and a slightly worse chance of ever learning anything about it. And we arrived at 2 systems, at 40 and 49 light-years, where the question is actually answerable. Which brings us to the obvious next step. Go and answer it. The technique is called transmission spectroscopy, and in principle it is one of the most elegant things anyone has ever thought of. When a planet transits its star, the star's light does not only get blocked by the planet's solid disk. A thin ring of light passes through the planet's atmosphere on its way to us, grazing the edge, travelling through a shell of gas maybe a few hundred kilometres thick, and coming out the other side altered. Molecules in that atmosphere absorb light at very specific wavelengths determined by their structure. Water absorbs in certain infrared bands. Carbon dioxide absorbs in others. Methane, oxygen, ozone, nitrogen, each has a signature. So if you measure the depth of the transit not as one number but as a spectrum, the depth at every wavelength separately, then at the wavelengths where the atmosphere absorbs, the planet appears very slightly larger, because the atmosphere is opaque there. The transit is a hair deeper, and the pattern of which wavelengths are deeper tells you in principle what the air is made of. We are reading the chemistry of another world in the shape of a shadow. It is a genuinely extraordinary idea, and it works. It has worked repeatedly on large, hot, puffy planets around bright stars where the signal is comparatively enormous. Now put the numbers to it for an Earth-sized planet. The transit itself is half of 1%. The wavelength-dependent variation on top of that, the actual atmospheric signal, is of order tens of parts per million. You're looking for a variation of a few thousandths of a percent in the depth of a dip that is itself 0.5%, in the light of a star 40 light-years away, and you have to do it repeatedly and stack the results, because a single transit does not come close to producing enough photons. And underneath the difficulty of the measurement sits a harder limit that no amount of engineering removes, which is simply that there are not enough photons. TRAPPIST-1 is an intrinsically faint object 40 light-years away. In any given second, only so many of its photons fall on the telescope's mirror, and you cannot manufacture more of them. To detect a signal of a few tens of parts per million, you need to count photons until the random statistical fluctuation in your count drops below that level. And because that fluctuation shrinks only as the square root of the number counted, halving your noise means quadrupling your observing time. The planet transits once every 6 days, and each transit lasts under an hour. So the total amount of usable data available in a year is measured in hours, and the only way to get more is to wait. There is no cleverness that shortcuts this. It is a queue, and the queue is set by the speed of light and the size of a mirror. That would be difficult if the star cooperated. The star does not cooperate. Red dwarfs are covered in star spots, regions of intense magnetic field where the surface is cooler and darker, and in faculae, which are the bright counterpart. The surface is mottled. And here is the problem, and it is subtle enough that it took the field years to fully appreciate it. A transiting planet does not pass across the whole face of the star. It crosses one chord, one narrow band. The light it blocks is the light from that band, and that band is not representative of the star as a whole. If the planet happens to cross a spotted region, or happens to cross a region that is unusually clear while the rest of the star is spotted, the fraction of light it blocks does not correspond to its size in the way the simple calculation assumes. This is called the transit light source effect, and it was described formally in 2018 by Benjamin Rackham, Daniel Apai, and Mark Jampapa. The consequence is severe. The star's own inhomogeneity imprints wavelength-dependent features on the measured spectrum. Star spots contain water vapor because they are cool enough for molecules to survive. So a spotted star can produce a water signature in a transmission spectrum of a planet that has no water and no atmosphere at all. In the TRAPPIST-1 system, stellar contamination is now the dominant systematic in every published transmission spectrum. Not one of several complications, the dominant one. The star is the loudest thing in the data about the planet. So what happened when the most powerful telescope ever built was pointed at the best habitable zone candidate in the sky? The James Webb Space Telescope observed transits of TRAPPIST-1e with its near-infrared spectrograph in a mode that spreads the light into a low-resolution spectrum, beginning with observations taken from the middle to the end of 2023. Results were published through 2025, including a set of 4 transits analysed together and further transits added subsequently, in a multi-cycle program committing on the order of 15 or more transits to this single question. An unusually large allocation of a resource that is oversubscribed by something like 9-1. The results are worth stating exactly, because the exactness is the point. A primary atmosphere, one dominated by hydrogen at 80% or more by volume, the kind a small planet would have kept from its formation, is ruled out at better than 3 sigma. Venus-like and Mars-like scenarios are disfavoured. Hydrogen-rich atmospheres with traces of methane and carbon dioxide are excluded. Nitrogen-rich atmospheres with traces of methane and carbon dioxide remain permitted, and that is all. The data do not lean strongly toward the planet having an atmosphere. They do not lean strongly toward it having none. After multiple observing campaigns with the most capable instrument our species has ever placed in space, aimed at the single best candidate in the sky, the honest summary is that we have ruled out several things it is not, and we still cannot say whether TRAPPIST-1e has air. More transits are scheduled. The answer may come. But notice what has happened to our question in the meantime. A candidate is not a destination. When we first said that several parts ago, it sounded like a caution about language, a bit of pedantry about not overselling. It is not pedantry. A candidate is not even a measurement. The quantity that would make a world a destination rather than a candidate is not currently obtainable for the best target we have, with the best instrument we have. And there is one further difficulty waiting at the end of all this, which is the strangest of the lot because it concerns what happens if the technique succeeds. Suppose the atmosphere is detected. Suppose, better than that, it contains oxygen. Oxygen has always been treated as close to a decisive signature. On Earth, atmospheric oxygen is maintained almost entirely by photosynthesis. Without continuous biological replenishment, it would react away into rocks and oceans within a few million years. Finding free oxygen on another world was supposed to be very nearly finding life. Work published in 2014 and 2015 by Sean Donegal Goldman and colleagues, and by Rodrigo Luga and Rory Barnes, showed several routes to substantial atmospheric oxygen with no biology involved at all. The most severe is exactly the one we described earlier, a planet around a red dwarf, cooked during the star's long luminous youth, with its ocean going into the atmosphere and ultraviolet light splitting the water molecules. The hydrogen escapes. The oxygen, being heavier, does not. Run that process for a few 100 million years, and you can build up an oxygen atmosphere of tens or even hundreds of bars on a completely dead, completely dry world. So the detection everyone is waiting for would not on its own settle anything. Distinguishing biological oxygen from the abiotic kind requires context. The simultaneous presence of a reduced gas like methane sitting in chemical disequilibrium with the oxygen, or the absence of the particular spectral signatures that dense oxygen atmospheres produce, or evidence of a surface ocean. Every one of those is a harder measurement than the oxygen detection that would have prompted the search, which means the instruments we have are not merely insufficient to answer the question, they are insufficient to interpret the answer if they got one, and the failure runs in the other direction too, which is the part that should genuinely unsettle you. Oxygen can appear without life, but life can also exist without oxygen appearing, and on the only inhabited planet anyone has ever confirmed, that was the situation for most of its history. Earth has been inhabited for something like 3.5 billion years. Free oxygen did not accumulate to significant levels in the atmosphere until the Great Oxidation Event around 2.4 billion years ago, and did not reach anything resembling modern concentrations until far more recently than that. So for roughly the first billion years of life on this planet, and arguably much longer, a survey identical to the one we are currently building would have looked at Earth, found no oxygen, and moved on. It gets stranger. The oxygen that finally made this planet detectable was, when it appeared, a poison. It was a waste product excreted by organisms that had no use for it, and its accumulation is thought to have driven one of the largest extinctions in the planet's history, killing off much of the anaerobic life that produced it. The signature that would let another civilization identify Earth as living is the residue of a catastrophe. So the criterion is unreliable in both directions at once. It can be present without life and absent with it. And that raises the obvious question, and it has a real answer, and the answer has a date attached to it. There is a strange kind of comfort in learning that a question is answerable. It converts a mystery into a schedule, and the question of whether any nearby world is habitable is genuinely answerable. The physics is understood, the techniques exist in principle, the targets have been identified. What is missing is not knowledge. It is glass, and money, and time. 3 enormous ground-based telescopes are currently in various stages of construction or planning. The extremely large telescope being built by the European Southern Observatory on a mountaintop in the Chilean Atacama has a primary mirror 39.3 meters across, assembled from 798 hexagonal segments. It is roughly the width of a football pitch, and it will collect more light than every existing large optical telescope on Earth combined. First light is targeted for around the end of this decade. The Giant Magellan Telescope at 25.4 meters uses 7 enormous circular mirrors in a flower arrangement. The 30-meter telescope at 30 meters has spent years without a settled sight. These instruments matter for our question because of a specific capability. At those apertures, with adaptive optics correcting the atmosphere's blurring hundreds of times a second, and with instruments designed to suppress the glare of a star, it becomes possible to separate the light of a planet from the light of its star, to look at a habitable zone planet around a nearby red dwarf directly, rather than inferring it from a wobble or a shadow. That is why the discovery paper for GJ251c framed it as an imaging target. That is what those telescopes are for. The instruments being designed for them have oxygen detection in nearby habitable zone planets as an explicit science goal. The requirement, though, is brutal. Tens to hundreds of nights of integration time per target, not hours. Nights, in the plural, adding up to months of the most contested observing time on Earth, spent on a single planet, to obtain a single answer that may then turn out to be ambiguous for the reasons we covered in the last part. And all of that applies to planets around red dwarfs, the ones with the flare problem, the tidal locking problem, the desiccation problem. For an actual Earth analogue, an Earth-sized planet in the habitable zone of a Sun-like star, none of these telescopes is enough. The contrast is too extreme, and the angular separation too small, and the atmosphere gets in the way no matter how good the correction is. For that, there is one plan, and it has a name. The Habitable Worlds Observatory was recommended by the 2020 Astronomy and Astrophysics Decadal Survey, the once-a-decade process by which the American astronomical community decides what to build next. It would be a space telescope somewhere around 6 meters in aperture, operating across the ultraviolet, visible and infrared, and its defining feature is starlight suppression. To see an Earth beside a Sun, you must reduce the star's light by a factor of about 10 billion, while preserving the planets, a contrast ratio of 1 part in 10 to the 10th. Consider what that means physically. You're trying to detect a firefly next to a searchlight, and you must do it while the telescope's mirror holds its shape stable to a fraction of a nanometer against thermal drift. There are 2 approaches to suppressing a star that much, and both are being studied. The first is a coronagraph, an arrangement of masks and mirrors inside the telescope that cancels the star's light through careful destructive interference while letting the planet's light through. It works, at least in the laboratory, but it demands that the incoming wavefront be controlled to a precision measured in picometers, thousandths of a nanometer, which means the entire optical assembly must be thermally and mechanically quiet to a degree no space telescope has ever achieved. The second is a starshade, a separate spacecraft tens of meters across, shaped with dozens of precisely engineered petals, flown tens of thousands of kilometers in front of the telescope so that it physically blocks the star while the telescope looks past its edge. The petal shape is not decorative. It is calculated to suppress the diffraction that a simple disk would produce. The engineering difficulty of that concept is not the shade. It is holding 2 spacecraft in formation, tens of thousands of kilometers apart, aligned to within a meter. The target list already exists, which is one of the quietly moving facts about this whole enterprise. Astronomers have compiled catalogues of the nearest stars suitable for such a survey. A few hundred candidates, ranked by how favourable their geometry and brightness would be, with the most promising couple of hundred studied individually for stellar activity, companions, and dust. Somebody has already made the list of addresses. The telescope that would knock on the doors is the part that has not been built. The stated primary science goal, which came directly out of the decadal process, is to detect and characterize 25 Earth-like planets in the habitable zones of nearby stars, and to search their atmospheres for biosignatures, oxygen, methane, water, and the vegetation red edge, which is the sharp rise in reflectance that chlorophyll-bearing surfaces produce just beyond visible red. That last one is a surface signature rather than an atmospheric one, and it would be among the most difficult and most unambiguous detections imaginable. 25, not 1. The mission is designed around a sample, because a sample is what converts habitability from an anecdote into a statistic, and because with a single detection, you can never be sure you did not find an unusual case. This is the instrument that would answer the question in the title, not the ground telescopes, not the James Webb Space Telescope, not anything that has ever been pointed at the sky. This one. Its launch is projected for the 2040s, and probably not before the first half of that decade. That date is not a placeholder, and it is not pessimism. It is deliberate. The decadal survey specifically recommended a slower path, with technology maturation completed before construction begins, precisely because of what happened with the last flagship. The James Webb Space Telescope was originally discussed for a launch around 2007 at a cost of around $1 billion. It launched at the end of 2021 at roughly $10 billion. The astronomical community looked at that and concluded that the next flagship should not be committed to a schedule before the hardest technologies were proven, even if that meant waiting longer at the start. So the verification distance, the second of the three numbers hiding inside our question, has a value, and here it is. To establish whether the nearest habitable zone planet is actually habitable requires an observatory that does not yet exist, whose launch is projected for the 2040s, followed by years of observation and analysis after that. Sit with the shape of that for a moment. The question of whether there is another place in the universe where a human being could live has been asked in one form or another for as long as anybody has looked up. It is now, for the first time in history, a question with a specific technical answer path and a specific expected completion date. And that date is far enough out that a substantial fraction of the people who care most about the answer will not be present to receive it. There is something particular about that shape of waiting. It is not the frustration of ignorance. We know how to find out. It is not the frustration of impossibility. Nothing forbids it. It is a scheduling problem, and the schedule is longer than a working life. People will spend entire careers building an instrument whose first meaningful spectrum will be read by someone who was not born when the project started. It is worth pausing on what that first image would actually look like, if it arrives. Not a photograph, not continents and cloud systems and a blue curve of ocean, a single pixel. One point of light, resolved apart from its star, holding steady and slowly, over weeks as the planet turns, varying in brightness and colour by a fraction of a percent as different surfaces rotate into view. From that variation, and from the way the light divides across wavelengths, you could infer oceans, land, cloud cover, seasons, possibly vegetation. An entire world reconstructed from the flickering of a single dot. That is the deliverable. That is what a generation of engineering is aimed at producing, and it would be, without any exaggeration, the most information-dense pixel in the history of the species. And even then, even with the Habitable Worlds Observatory operating perfectly, even with a clean detection of oxygen and methane and water in chemical disequilibrium around a sun-like star 20 light-years away, even with the vegetation red edge showing up in the reflected light, you would still not be finished. Because you would then know, with reasonable confidence, that there is a living world at a particular address, and you would have absolutely no way of going there, which is the third number, and it is much, much larger than the other two. Here is where the question changes units. Everything so far has been measured in light years, which is a length. But a length only becomes meaningful when you know how fast you can traverse it, and the moment you introduce a speed, the light year stops being a distance and becomes a duration. The conversion rate is not fixed. It depends entirely on what you are willing to build, which means that the distance to the nearest habitable planet is, in a very real sense, a number we set ourselves. So let us set it, using every method that has ever been seriously proposed and see what comes out. The baseline is Voyager 1. It launched on the 5th of September 1977, and it is now moving away from the Sun at about 17 kilometers per second. That is roughly 61,000 kilometers an hour, which sounds enormous and is, in every context except this one. As a fraction of the speed of light, it is 0.0057%. At that speed, a target 20 light-years away, the figure we will be coming back to at the end of tonight, is about 350,000 years away. Not a rounding of history. Longer than anatomically modern humans have existed. Longer than our species has had language, agriculture, cities, or memory. If a Voyager-class craft had been launched toward a habitable world at the moment the first modern humans appeared in East Africa, it would be arriving approximately now. Somebody always says, but Voyager is old. And that is true, and it is also almost irrelevant. The fastest object humans have ever built is the Parker Solar Probe, which has reached about 192 kilometers per second at its closest approach to the Sun. That is more than 11 times Voyager's speed, and it is still only 0.064% of light speed. And, this is the part that matters, that velocity is borrowed. It is the speed of something falling deep into the Sun's gravity well, which the probe pays back on the way out. It is not a departure velocity. You cannot leave the solar system on it. The obstacle is not engineering ambition. It is an equation published in 1903 by Konstantin Tsiolkovsky, working in near-total obscurity in provincial Russia, and it is one of the most consequential and most unforgiving statements in all of physics. The rocket equation says that the velocity a rocket can reach depends on two things: the speed at which it throws its exhaust out the back, and the ratio between its fueled and unfueled mass. And critically, the relationship with that mass ratio is logarithmic. which means the relationship running the other way is exponential. Every increment of extra speed costs exponentially more fuel, and that fuel has mass, which must itself be accelerated. Chemical rockets have exhaust velocities of around 4.4 kilometers per second. That number is not a matter of engineering quality. It is set by the energy released per unit mass in a chemical bond, and chemical bonds have the energies they have. To reach even 10% of light speed with chemical propulsion, you would need a mass ratio of the mathematical constant E raised to a power of roughly 6,800. That is a number with thousands of digits. It exceeds the mass of the observable universe by a margin that has no useful comparison. Chemical rockets are not slow for interstellar purposes. They are excluded, categorically, permanently, by arithmetic. Every serious proposal since has therefore been nuclear. Project Orion was studied between 1958 and 1963 at General Atomics, with Freeman Dyson and Ted Taylor among its leading figures. The concept was almost aggressively direct. Detonate shaped nuclear charges behind a heavy pusher plate and ride the shock waves. Interstellar variants contemplated a few % of light speed and hundreds of thousands of bombs. The program built exactly one piece of hardware, a chemically propelled test model, informally called Hot Rod, which flew in 1959. Orion ended in part because the 1963 Partial Test Ban Treaty prohibited nuclear detonations in space. Dyson later described it as the only propulsion concept he knew of that could have put humans on the outer planets within his own lifetime, and also as something he was relieved had never been built. Project Daedalus was developed by the British Interplanetary Society between 1973 and 1978, and it remains the most thoroughly engineered interstellar design ever produced. A two-stage vehicle using inertial confinement fusion with a total mass of about 54,000 tons, of which roughly 50,000 tons was fuel, deuterium and helium-3, the helium-3 to be mined from the atmosphere of Jupiter, because there is no meaningful supply of it anywhere closer. It would have reached about 12% of light speed, and it was designed for a flyby of Barnard's star 6 light-years out. A flyby, not an arrival. Daedalus had no deceleration stage at all, because adding one would have roughly squared an already impossible fuel requirement. It would have crossed its target system in a matter of hours, taking data the entire way, and then continued outward forever. At Daedalus speed, 20 light-years takes about 167 years, and you do not stop. The most recent serious attempt was announced in April of 2016, with considerable ceremony. Breakthrough Starshot, backed by Yuri Milner with Stephen Hawking and Mark Zuckerberg on its board, was a $100 million research program towards something genuinely clever. Abandon the idea of carrying fuel altogether. Build a laser array on the ground with a total power of around 100 gigawatts, comparable to the entire electrical generating capacity of a mid-sized industrialized nation, and focus it on a sail of a few square meters carrying a payload weighing a gram. Accelerate it to 20% of light speed over a few minutes, 20-year transit to Proxima, then 4.25 years for the data to come back at the speed of light. It had no brakes either. The entire mission was a few hours of measurements at 20% of light speed, followed by a radio whisper home from a transmitter the size of a postage stamp. By September of 2025, Breakthrough Starshot had been placed on indefinite hold. There was no announcement, no final report, no ceremony to match the launch. Activity had peaked around 2020 and 2021. Funding thinned, meetings stopped, communications quietly ended. Public accounting indicates that of the $100 million pledged, something on the order of $4.5 million was actually spent across roughly 30 contracts. That is worth stating plainly, because it is the single most informative data point in this entire part. The most ambitious interstellar program of the century did not fail on physics. Nothing in it was shown to be impossible. It failed on money and attention, which are, it turns out, considerably scarcer resources than either. There is also a problem with going fast that has nothing to do with fuel, and it gets worse the better your propulsion works. Interstellar space is not empty. It contains dust, grains of silicate and carbon, most of them smaller than a micron, at densities so low that a cubic kilometre might contain only a handful. At walking pace, this is irrelevant. At 20% of light speed it is not, because kinetic energy scales with the square of velocity, and a micron-sized grain arriving at 60,000 kilometers per second carries the energy of a small bullet concentrated into a point smaller than a bacterium. Over a 20 light-year crossing, A sail a few meters across would be struck by an enormous number of them. Nobody has ever tested a material against that environment because nothing on Earth can produce it. The proposed solutions involve flying edge-on, or accepting erosion, or carrying a sacrificial forward shield, which is mass, which brings you straight back to the rocket equation. Beyond fusion there is one more rung, and it is the theoretical ceiling for anything that works by throwing mass backward. Antimatter annihilation converts mass to energy at essentially 100% efficiency. 1 gram of antimatter meeting 1 gram of matter releases about 1.8 times 10 to the 14th joules. It is the most energy-dense reaction physics permits. Current global production of antimatter at facilities like CERN is measured in nanograms per year. Estimates of the cost per gram run into the tens of trillions of dollars. A relativistic crewed mission would require tonnes, and underneath all of the propulsion questions sits a simpler one that no amount of cleverness escapes, which is the raw energy budget. Accelerating a 1,000-ton vehicle, modest, by the standards of anything that could carry people for centuries, to 10% of light speed requires on the order of 4.5 times 10 to the 20th joules. That is comparable to a substantial fraction of the total annual energy consumption of human civilization. All of it. Every power station, every engine, every furnace for a significant portion of a year poured into one object, and that figure is for acceleration only. Stopping at the other end doubles it, unless the craft can brake against the destination star's radiation and stellar wind using a magnetic sail. An elegant concept that has never been tested, and that would, in any case, only work well if you are arriving somewhere with a strong stellar wind, which the quiet red dwarfs we would most want to visit specifically do not have. So there is the third number, at least in its first form. To reach a habitable world 20 light-years away requires either a few 100,000 years, using anything that has ever actually flown, or roughly a century and a half using a design that was fully engineered 50 years ago, was never built, and could not have stopped when it arrived. Which leaves the question that everyone eventually arrives at. If the journey takes centuries, then perhaps the answer is not to make the journey shorter. Perhaps the answer is to make the travellers last longer. There are 3 ways to survive a journey that is longer than a life, and each of them solves the problem by getting rid of something. The first gets rid of the individual and keeps the population. If the voyage takes 400 years, you do not need anyone to live 400 years. You need a community that can reproduce itself across 16 or 20 generations inside a sealed vessel, arriving with descendants who share almost nothing with the people who left except a mission statement. The question of how many people that takes has actually been studied properly, which surprises people. Frédéric Marin, an astrophysicist at the Strasbourg Astronomical Observatory, and Camille Belloufi, a particle physicist, built a stochastic Monte Carlo code called Heritage, which simulates a closed population across a multi-millennial voyage, testing randomized outcomes for pairings, births, deaths, accidents and disease over and over to see which starting configurations survive. Their result, published in 2018, was that the minimum viable crew is about 98 people, under strict rules governing who may have children with whom, in order to avoid the accumulation of genetic disorders from inbreeding across generations. 98. A number small enough to be genuinely surprising. Subsequent work raised the recommended figure substantially, to around 500, to provide margin against catastrophe, disease outbreaks, and the ordinary bad luck of small populations. A follow-up study calculated that a crew of 500 would require roughly 0.45 square kilometers of artificial farmland using a combination of aeroponics and conventional agriculture to feed itself indefinitely. Other researchers, including the anthropologist Cameron Smith, have argued for populations in the range of 10,000 to 40,000, not for genetic reasons but for cultural ones, on the grounds that a small isolated group loses knowledge, skills and social complexity over generations in ways that a large one does not. But the population is not the hard part. The hard part is the box. Between 1991 and 1993, 8 people sealed themselves inside a structure in the Arizona desert called Biosphere 2. 3.14 acres of engineered biomes under glass, containing a rainforest, a savanna, a mangrove wetland, a small ocean with a coral reef, and agricultural land. It was the most serious attempt ever made at a closed ecological system, and it was intended to run for 2 years. Within 16 months, atmospheric oxygen had fallen from 20.9% to 14.5%. That is the equivalent of being at an altitude above 4,000 meters. The crew were experiencing chronic fatigue and sleep apnea, and oxygen had to be injected from outside. The cause was eventually traced to a combination of microbial respiration in the unusually rich soil and, of all things, the uncured concrete of the structure absorbing carbon dioxide, which broke the loop that would have returned oxygen to the air, a system that failed in 16 months, with an entire planet available for rescue and a team of engineers outside watching. The crew also fractured socially, reportedly splitting into two factions that stopped speaking to one another, which is a data point about closed human systems that no engineering review captures and no simulation currently models. The International Space Station does considerably better at the machinery. Its environmental control systems recover on the order of 98% of water and about half the crew's oxygen. Those are extraordinary numbers, achieved through decades of iteration. They are also numbers for a system designed to be resupplied every few months, with spare parts arriving from a factory in a vehicle that can be evacuated in hours. Losing 2% of your water per cycle is nothing over 6 months. Over 400 years, it is everything. Let me put you inside the answer to all this. You are somewhere near the middle of the voyage, 200 years out, 200 to go. A person is born here today who will live a complete human life, childhood, work, love, age, death, without ever standing on a planet. Their sky is a curved ceiling 12 meters up, lit on a schedule. Their horizon is the end of a corridor. They know what wind is as a word. They have seen recordings of rain. Behind them, if they go to the aft observation port, there is a bright star. That is the sun. It is not distinguishable by eye from any of the several hundred other bright stars around it. Ahead, at the forward port, there is another bright star, slightly different in colour. That is the destination. It is also not distinguishable by eye from anything else. Both are just points. The entire journey from inside looks like nothing happening. They did not choose this. Their great-great-grandparents chose it, on a planet this person will never see, for reasons recorded in an archive. Their whole contribution to the mission, the entirety of what their life is for structurally, is to keep the population viable and the machinery running for one more generation and to hand it on. And they are one of perhaps 16 generations who will do exactly that. That is the shape of the thing. Every previous frontier in human history was crossed by people who saw the other side. Somebody stood on a beach they had sailed toward. Somebody walked over a mountain pass and looked down. The crossing and the arrival happened to the same person, and that is so fundamental to what exploration means that we do not have a word for the alternative. This is the first frontier where the crossing and the arrival cannot happen to the same person, which means the distance to the nearest habitable planet is not really measured in kilometers or even in years. It is measured in the number of complete human lives it consumes on the way. And notice that we have been discussing all of this as though the destination were known to be worth arriving at. It is not. Everything in the first half of tonight applies here with full force. The mission that departs will be aimed at a planet whose atmosphere was inferred from a spectrum, whose surface has never been imaged, whose composition rests on a density measurement and a population statistic. 16 generations would be spent travelling toward a candidate, and the confirmation, the moment when someone finally learns whether the place is a world or a rock with an oxygen atmosphere and no water, would arrive at the very end, delivered to people who had no say in the decision and nowhere else to go. So the second approach gets rid of the time instead of the individual. If a person could be suspended, metabolism slowed to a fraction, aging effectively paused, then the same people who left could arrive. The research here is real, and it is more advanced than most people realize. The European Space Agency has run a formal assessment of torpor for deep space missions, and the target most often cited is reducing metabolic rate to about 25% of normal. The gains would be enormous: dramatically less food, water and oxygen, a much smaller habitat, and the removal of the psychological load of years of confinement. Estimates suggest habitat mass reductions of roughly a third to a half for a Mars mission alone. A shallow metabolic depression of around 20% is considered the feasible first step, testable on short flights. Concepts funded through NASA's Advanced Concepts program have sketched torpor habitats using targeted temperature management down to around 32 to 34 degrees Celsius, sedation, and intravenous feeding in rotating cycles of about 2 weeks. Some researchers have suggested that first human trials could be feasible within a decade, and the biology is genuinely encouraging. Bears hibernate for 5 to 7 months with a core temperature drop of only about 5 degrees and emerge with their bone density and muscle mass largely intact, a feat that medicine cannot currently replicate and would very much like to understand, because it would transform the treatment of immobilized patients. Arctic ground squirrels go further, dropping their body temperature below the freezing point of water without freezing. But the gap between that and what a voyage requires is not a gap of degree. The longest documented therapeutic hypothermia in a human being is measured in days to about 2 weeks, not months, not years, and no known mechanism protects a torpid human from the cumulative dose of galactic cosmic radiation over a voyage lasting centuries, heavy nuclei that pass straight through shielding and, worse, shatter it into secondary particle showers that can be more damaging than the original flux. True cryonic suspension is further away still. Vitrification, cooling so fast that water becomes glass rather than ice, avoiding the crystals that destroy cells, works, but it requires cryoprotectant concentrations that are themselves toxic. The largest mammalian organ ever vitrified, cooled, rewarmed, and successfully transplanted back into a living animal is a rabbit kidney, demonstrated in 2009. A kidney. Nothing larger has been brought back. Which leaves the third approach, and it is the one that gets rid of the passengers entirely. Send frozen embryos, let a machine gestate them on arrival and raise them. The concept has been sketched seriously in the literature. It depends on an artificial womb for humans, and the state-of-the-art there is a sealed, fluid-filled system that sustained extremely premature lambs for about 4 weeks in 2017. 4 weeks for a lamb. There is no human artificial womb, and no machine has ever raised a child. And there is one more argument which is not about biology or engineering at all, and which quietly undermines every version of the plan. It was formalized in 2006, and it is usually called the weight calculation. Suppose our ability to travel keeps improving, as it has for the past few centuries. Then a ship launched today, crawling along at whatever speed today's technology permits, may be overtaken en route by a ship launched 100 or 300 years later using better technology. The later ship departs long after and arrives long before. The first crew, 12 generations of them, spend their entire existence in a corridor and are passed somewhere in the dark by people who left after their descendants were born. Run the arithmetic under plausible rates of technological improvement, and something genuinely uncomfortable falls out. For a voyage of 1,000 years, the rational departure date can be several hundred years in the future, which means that at any given moment, the correct decision, the one that gets a human being to the destination soonest, may be to not go. And it may remain the correct decision indefinitely, because the argument regenerates itself every time you make it. A civilization could reason its way, entirely correctly, into never leaving at all. That is the incentive trap, and it does not require anyone to be cowardly or short-sighted or poor. It only requires them to be sensible. So, keep the population and lose the individuals. Keep the individuals and lose the biology. Or lose the people altogether and hope the machines can make new ones. Every one of them is a way of admitting that the distance is longer than a life, unless, of course, you could simply refuse the distance. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a short paper in the journal Classical and Quantum Gravity, and it did something that had not quite been done before. It took an idea from science fiction and wrote it down as a solution to the Einstein field equations. The trick is beautifully simple once you see it. Relativity forbids anything from moving through space faster than light. It says nothing at all about how fast space itself can move. Space expanded far faster than light during cosmic inflation, and distant galaxies are receding from us faster than light right now. And neither of those violates anything, because the objects are not moving through space. The space between us is growing. So, do not move the ship, move the space. Alcubierre's solution describes a bubble of ordinary flat space-time, with the space-time immediately ahead of it contracting, and the space-time immediately behind it expanding. The bubble is carried forward by that asymmetry. Anything inside it is in free fall the entire time, never accelerating, never experiencing any force, never exceeding light speed relative to its own local surroundings, while the bubble as a whole crosses arbitrary distances in arbitrarily short times. Let me put you inside it. You are seated. There is no thrust. There is no vibration, no press into the back of the chair, No sensation of motion of any kind, because there is none. Locally you are at rest, and you have been at rest since the moment the field came up. If you released a pen, it would hang exactly where you left it. Outside the forward window, the destination star is growing. Not slowly. It is swelling perceptibly, a point becoming a disk, becoming a sun, and the pattern of stars around it is distorting into a ring as the geometry ahead of you folds inward. You cross 20 light-years without your body ever exceeding the speed at which you would walk across the cabin. The clock on the wall keeps ordinary time. Nobody ages strangely. You will arrive before the light that left the destination when you departed, and then somebody hands you the invoice. To hold that bubble open, the equations require a very specific ingredient, and it is not an engineering material. It is negative energy density, a region of space containing less than nothing, less energy than empty vacuum, exotic matter in the standard terminology. The original solution's requirement was estimated at more than the mass energy of the observable universe, expressed as a negative quantity. Chris van den Broek published a modification in 1999 that reduced that by many orders of magnitude, and later optimizations brought it further down still. Alcubierre himself has cited figures on the order of 100 Jupiter masses of negative energy for a bubble 100 meters across, and has described a practical drive as very unlikely. 100 Jupiter masses of a substance nobody has ever produced in more than the most fleeting laboratory quantities. That is the optimistic figure. That is after the improvements. But the field has genuinely moved, and it deserves an honest account, because the story is more interesting than a flat dismissal. In 2021, Alexei Bobrik and Gianni Martia published a paper titled Introducing Physical Warp Drives, which reframed the entire problem. They showed that the Alcubierre solution is one member of a much larger family of warp geometries, and that within that family, subluminal warp bubbles can in principle be constructed using purely positive energy density, no exotic matter at all. They also reduced the negative energy requirement for the superluminal cases by around 2 orders of magnitude. The same year, Eric Lentz proposed soliton solutions that he argued could be sourced by positive energy matter in a plasma state while still exceeding light speed. That claim has been contested repeatedly since. Analyses by Santiago, Schuster and Visser argued that generic warp drives violate the null energy condition regardless of construction, and later work found weak energy condition violations in the Lentz solution specifically. And in 2024, a team led by Jared Fuchs at Applied Physics, working with researchers at the University of Alabama in Huntsville, published something genuinely notable, a constant velocity physical warp drive that satisfies all of general relativity's energy conditions, requiring no exotic matter whatsoever. A real, buildable in principle warp geometry. It is strictly subluminal. It cannot beat a photon, and there is the pattern, running consistently across 3 decades of serious work. Every single step toward physical realizability has been paid for by giving up the faster-than-light part. The solutions that go faster than light need substances that may not exist. The solutions that use only substances that do exist do not go faster than light. Nobody has shown that this trade is a theorem, but nobody has ever escaped it either, and the consistency of it across independent groups working from different starting points is itself a form of evidence. It is worth pausing here on a claim that circulates persistently, because the honest answer to it is more interesting than a dismissal. The claim is that faster-than-light propulsion already exists, quietly, inside classified programs, and it is usually anchored to a genuine fact, which is that the Alcubierre metric is real physics published in a real journal. Sometimes it points to patents, including a set filed on behalf of the United States Navy in the late 2010s, describing a high-frequency gravitational wave generator and an inertial mass reduction device. The seed of truth is real, and it should be acknowledged. The mathematics of warp geometries is legitimate, peer-reviewed, and actively worked on. But a patent is a legal document describing a claimed invention. It is not a demonstration, and patent offices do not test whether a device functions. The Navy's own technical reviewers raised feasibility objections in correspondence that has since been released, and no peer-reviewed measurement of any space-time engineering effect has ever been published, by anyone, anywhere. More to the point, the obstacle here has never been cleverness or secrecy. It is the energy conditions, constraints on what kinds of matter and energy the universe appears to permit. A classified program does not get to have different physics. If somebody had found a way around the energy conditions, that result would be one of the most important in the history of the subject, and it would not stay quiet because the theorists who would need to check it are scattered across a dozen countries and publish for a living. Wormholes follow the same arc, almost beat for beat. The Einstein-Rosen bridge, described in 1935, is a genuine feature of the mathematics of black holes, a connection between two regions of space-time. It is also non-traversable. It pinches shut faster than anything, including light, could cross it. It is a tunnel that closes before you enter it. In 1988, Michael Morris and Kip Thorne published the analysis that established what a traversable wormhole would actually require. Thorne had been asked by Carl Sagan for a scientifically defensible way to move a character across the galaxy in a novel, and the request turned into serious research. The answer: you can hold a wormhole open, but only by threading its throat with exotic matter. The same negative energy density the warp drive needs, for the same reason. Gravity pulls the throat closed. Something with the opposite sign has to hold it apart. Quantum field theory does permit negative energy densities in small amounts. The Casimir effect, in which two uncharged conducting plates placed extremely close together experience an attractive force because the vacuum between them is restricted, is a measured, laboratory-confirmed example of a region with less energy than empty space. It is real. It is also, in magnitude, absurdly, hopelessly small. The effect is measured in tiny fractions of a joule per cubic meter, and there are limits on how much you can have. Quantum inequalities derived by Ford and Roman constrain the amount of negative energy that can exist in a region and how long it can persist. The more negative energy you concentrate, the more briefly it can last, and the constraint is severe. For a wormhole throat large enough to pass a human being, the requirement works out to something like a planetary mass of negative energy, confined to a shell perhaps 10 to the minus 21 meters thick. That thickness is far smaller than a proton, and there is a final objection, which is less a calculation than a suspicion held by some very serious people. Anything that can travel faster than light between 2 points can, under the right arrangement of reference frames, be used to send a signal into its own past. Faster-than-light travel and time travel are the same capability wearing different clothes. Stephen Hawking proposed in 1992 what he called the chronology protection conjecture, that whatever the correct theory of quantum gravity turns out to be, it will contain some mechanism forbidding the closed time-like curves that these solutions permit, that the universe, as he put it, is safe for historians. That is a conjecture, not a proof. Nobody has demonstrated it. But it names the suspicion accurately. The shortcuts may not be blocked by our engineering. They may be blocked by the structure of causality itself. So we have now tried every door, the nearest candidate and the ladder outward, and the instruments, and the fuel, and the crews, and the sleepers, and the embryos, and the folded space, and the tunnel, which leaves nothing to do but answer the question. There is a way to answer the question without finding the planet first, and it is worth understanding, because it is where the real number comes from. The quantity you need is called eta Earth. It is the fraction of stars that host an approximately Earth-sized planet in their habitable zone. If you know that fraction, and you know how many stars there are per unit volume in the neighborhood, then the expected distance to the nearest such planet falls straight out of the geometry. You do not need to have found it. You only need to know how common they are. So what is eta Earth? Nobody agrees. Published estimates for Sun-like stars span more than a factor of 10. The low-end analyses give values around 0.05, the middle cluster near 0.1, the high-end gives 0.36 or 0.54, or ranges running from 0.37 up to 0.6. One widely cited early result put 22% of Sun-like stars in the category. A more recent analysis focused specifically on G-type stars gives about 7.5%. The reason for the spread is structural, and by now it should sound familiar. Kepler was never quite sensitive enough to reliably detect an Earth-sized planet on a one-year orbit around a Sun-like star. Such a transit is 84 parts per million deep and happens once a year, so a 4-year mission sees at most 4 of them, and the smallest, most Earth-like signals are exactly the ones that sit closest to the noise. Every published value of eta Earth is therefore an extrapolation from planets that were somewhat larger or somewhat closer in, or both, out into the regime nobody actually sampled properly. and the extrapolation is extremely sensitive to how you define Earth-sized and how you define the habitable zone. Switching from the conservative zone to the optimistic one can move the answer by a factor of 2 before you have changed anything else. And yet, and this is the part that makes the whole exercise work, the distance that comes out is remarkably stable. The reason is a piece of geometry that is worth carrying with you. The expected distance to the nearest example of anything scales as the inverse cube root of how densely those things are packed. Cube root, so a factor of 10 of uncertainty in how common habitable planets are becomes only a factor of about 2.15 in how far away the nearest one is. You can be badly wrong about the abundance and still be roughly right about the distance. So here is the number. Converting the Kepler occurrence rates to the local stellar census gives an average distance to the nearest habitable zone rocky planet around a G or K dwarf, a star reasonably like the Sun, of about 6 parsecs. 6 parsecs is approximately 20 light-years. The same analyses suggest there should be something like 4 habitable zone rocky planets around Sun-like stars within 10 parsecs, and a reasonable probability that the nearest of them lies within about 12 light-years, roughly 3.7 parsecs, 20 light-years. That is the answer to the question in the title, in the only form it can currently be given, and now the 3 qualifications that turn that number from a fact into something considerably stranger. The first, that planet has not been found. The number is a prediction, not an observation. Somewhere within about 20 light-years of here on the current best statistics, there is a rocky world of roughly Earth's size in the temperate zone of a reasonably sun-like star, and nobody knows which star it is. It is not on any list. It has no name. The catalogue we spent the first half of tonight walking through, Proxima b, Ross 128b, T-Gardens b and c, GJ 251c, Wolf 1069b, Gliese 12b, Trappist 1e, LHS 1140b, is not the catalogue of what is out there. It is the catalogue of what our instruments happen to be able to reach. The best candidate is almost certainly something we have not detected yet, orbiting a star you could point at tonight. The second, even if it is found, we cannot currently confirm it. The verification distance is not measured in light years, it is measured in decades and in one telescope that does not exist. The Habitable Worlds Observatory, 25 target planets, 1 part in 10 billion of starlight suppression, projected for the 2040s. That is the earliest date at which anyone could say with real confidence that a specific address 20 light-years away has water and air and something living in it. The third, even confirmed, we cannot reach it. 350,000 years at the speed of the fastest thing we have ever launched. 167 years at the speed of a fusion design that was never built and could not have stopped. 16 generations in a sealed corridor, a dozen human lifetimes minimum consumed by the crossing. So the honest answer to how far the next habitable planet really is has 3 numbers in it, and only one of them is a distance. 20 light-years in space. 20 years or more in instrumentation before anyone could confirm it, and centuries, at the absolute best with technology nobody has built, to arrive. And 2 of those 3 numbers are not facts about the universe at all. They are facts about us. They are functions of what we choose to build and fund and finish. The geometry is fixed. The rest of the distance is a decision, renewed or declined every year, by people who mostly are not thinking about it. Which brings us back to where we started, 4.24, the number everyone repeats, the one that sounds almost close, the one that gets quoted whenever anyone asks how far the nearest other world is. We know now what it actually measures. It is the distance to a star. It was never the distance to a habitable planet, because nobody has established that there is one there, and the more you learn about Proxima Centauri, the locking, the flares, the 14,000-fold ultraviolet event in 7 seconds, the ocean that may have boiled off before the star ever settled down, the less likely it looks. The number was correct, and it was answering a question nobody had asked, and underneath all of it sits the dip. 0.5% of a star's light, going missing for under an hour, once every 6 days, 40 light-years away. That is the entire evidentiary foundation for the best candidate anyone has. Every argument tonight, every distance, every plan for crossing, every hope attached to every rung of that ladder, all of it traces back to shadows of that depth and to statistical extrapolations from a survey that could not quite see the thing it most wanted to find. We have built an enormous structure of expectation on top of a very small quantity of light. There is one more thing worth saying, and it is the thing that reframes the entire question rather than answering it. Everything tonight has assumed that habitable means a surface, warmed by a star, at the right distance. But the two most promising candidate habitats for life in our own solar system are not in the habitable zone and never have been. Europa holds a liquid water ocean beneath its ice, containing perhaps 2 or 3 times the volume of all of Earth's surface water, heated not by sunlight but by the tidal flexing of Jupiter's gravity. Enceladus, a moon 500 kilometers across, small enough to sit inside a single American state, is venting the contents of its subsurface ocean into space through cracks at its south pole, and the Cassini spacecraft flew through that plume and found molecular hydrogen, silica nanoparticles, and complex organic molecules. Both of them are hundreds of millions of kilometers outside anything the habitable zone concept would include. If life exists anywhere else in this solar system, the leading candidates are places our entire search strategy would exclude by construction, which means the distance to the nearest habitable world might not be 20 light-years at all. It might be about 600 million kilometers, straight down through an ice shell, in a place we have been treating as irrelevant because it is dark. And there is a reason that possibility matters more than it first appears. Every estimate in this video, every occurrence rate, every extrapolation, every argument about what counts as habitable, is built on a sample size of 1. We have exactly one example of a living world, and we have generalized from it relentlessly, because there was nothing else to generalize from. Liquid water on a surface, a star at a moderate distance, an atmosphere at roughly 1 bar. Those are not the requirements for life. They are the specifications of the only instance we have ever examined. A single microbe found under the ice of Europa would change that more than any telescope ever built. Not because a microbe is impressive, but because 2 data points make a distribution where one makes only a description. It would tell us whether life needs a star at all, whether it needs a surface, whether the entire habitable zone framework has been a parochial assumption dressed up as physics for 60 years. And unlike a planet 20 light-years away, that answer is reachable. There are spacecraft designed for it. It is a matter of decades and funding, not of centuries and exotic matter. Which is a strange thought to hold alongside everything else tonight, that the fastest route to understanding how far the nearest habitable planet is might not involve looking outward at all, and that is the shape of the real answer, not a number, a confession. After 30 years of searching, more than 6,000 confirmed planets, purpose-built spectrographs, a $10 billion space telescope, and the finest instruments our species has ever constructed, the number of planets anyone has ever confirmed to be habitable is 1. You are on it. It is the only address in the universe that has ever been verified, and everything else in this video is a measurement of how far away the second one might be. A number that is small enough to sound close, large enough to be uncrossable, and uncertain enough that nobody can yet tell you whether the place it points to is a world or a warning. That is the terrifying truth about how far the next habitable planet really is. Not that it is far. Distance on its own we could learn to live with. It is that the distance is not finished being decided.